Arduino is a fantastic tool for electronics. Many engineers and hobbyists start their journey with it. The platform excels at making complex concepts accessible. You can rapidly test a new idea. You can build a functioning proof of concept in just a few hours. This speed is invaluable during the initial phases of exploration. The vibrant community. The vast library ecosystem provides support for almost any simple project you can imagine. It lowers the barrier to entry, allowing people to bring their digital creations to life without needing a deep background in electrical engineering. However, building a commercial product is a different challenge. A product is not a demonstration. It must operate reliably and predictably for years. Design intent is a crucial concept in professional engineering. It refers to the conscious and deliberate choices made to meet specific product requirements. The Arduino ecosystem is intentionally built to obscure many of these choices. This is a feature, not a bug, for its target audience. Beginners can blink an LED without understanding. Clock configuration pin, multiplexing, power-on sequencing. The libraries and board support packages handle these complex details in the background. This abstraction layer is what makes Arduino so powerful for getting started quickly. It lets you focus on the what instead of the how. This convenience, however, comes at the cost of control. When you build a product, you must be the master of these details. You cannot afford to have them hidden. For example, you must intentionally select the system clock source and the system clock speed to balance performance against power consumption. You need to control pin drive strength and slew rates to manage signal integrity and electromagnetic interference, EMI. A simple demonstration can often tolerate inconsistent timing. An LED that blinks a little too fast or slow is still a success. A product, on the other hand, frequently demands precise and predictable timing. This is known as determinism. Many standard Arduino functions introduce significant and often unpredictable delays. The delay function is the most famous example. It completely halts CPU execution, preventing the system from responding to any other events. This is rarely acceptable in a product that needs to multitask or react quickly to user input. Many Arduino libraries are also guilty of introducing timing unpredictability. They often use blocking I/O calls, which means the program waits idly while a sensor takes a reading or data is sent over a serial port. Worse, many libraries configure hardware timers and interrupts behind the scenes. This can lead to subtle and frustrating conflicts. One library might configure a timer for its own purpose, only to have another library reconfigure that same timer, breaking the first library's functionality. This lack of a unified timing architecture makes it very difficult to build a system that can reliably perform multiple time-sensitive tasks simultaneously. In a professional product, timing is not an afterthought. It is a core design parameter. You may need to sample an analog sensor at a precise, consistent rate to perform a fast Fourier transform, or FFT. You might need to generate a PWM signal with very low jitter to control a motor smoothly. You may need to guarantee a maximum response time to an external trigger. To achieve this, engineers need direct control over the microcontroller's hardware timers, interrupts, and clock systems. They write non-blocking code that allows the CPU to perform other work while waiting for I/O operations to complete. Professionals use tools and techniques to validate timing. They explicitly configure hardware timers and direct memory access, DMA, controllers to handle data transfers without CPU intervention. This offloads work from the processor and ensures that data movement happens with predictable latency. They carefully manage interrupt priorities to ensure that the most critical events are serviced first. This rigorous approach to timing is what separates a hobby project from a robust, reliable product. During development, an Arduino is almost always powered by a USB cable. This provides a clean, stable 5-volt supply with plenty of current. It is a forgiving environment that hides many potential power-related problems. The linear regulators found on many Arduino boards are simple and sufficient. LEDs, sensors. However, they are often inefficient and not designed for battery-powered or power-constrained products. Their limitations become apparent when you unplug from the wall and try to run on a small battery. Real products, especially portable or battery-operated ones, require meticulous power supply design. Engineers must think in terms of microamps, not just milliamps. Every component's power consumption in both active and sleep modes must be accounted for. The efficiency of voltage regulators, their quiescent current, their dropout voltage become critical parameters. A brownout, a temporary dip in the supply voltage, can cause a microcontroller to reset or behave erratically. A professional design includes brownout detection circuits to ensure a graceful shutdown or reset, something that is not always robustly handled on a standard Arduino board. Furthermore, the Arduino ecosystem of shields can introduce unforeseen power issues. A shield might draw a significant amount of power even when its features are not being used. The combined sleep current of an Arduino stacked with several shields can be surprisingly high, draining a battery in hours, instead of days or months. In a custom product design, power is managed with much greater precision. Engineers implement power gating. They use ultra-low power sleep modes, waking only when necessary via interrupt or a real-time clock. It involves careful PDN design, efficient switching regulators, specialized tools like SMUs to measure nanoamps, and analyzing real-world power profiles to predict battery life. This is essential for longevity and performance. Print. For many Arduino users, debugging begins and ends with serial.print. Placing print statements throughout the code lets you see the value of variables. Placing print statements lets you trace the program's flow. This method is simple and intuitive, and it works reasonably well for small, simple projects. However, it has severe limitations that make it unsuitable for debugging complex products. The act of sending serial data takes time. Adding numerous print statements can significantly alter the timing of your program. This can hide timing-sensitive bugs, like race conditions, or even create new ones that only appear when the debug code is present. In a professional environment, engineers need more powerful debugging tools. They need to see what the processor is doing in real time without intruding on its operation. This is accomplished using hardware debug interfaces like serial wire debug or JTAG. These are dedicated ports that allow a probe to connect directly to the CPU core. With this, an engineer can pause execution at a breakpoint, inspect CPU registers, memory locations, and peripheral status registers. You can step line by line or instruction by instruction, analyze the call stack, monitor the heap for leaks, and set watch points that halt when a variable changes. Advanced tools add trace, serial wire viewer, or embedded trace macro cell can stream data in real time, logging variables, recording events, and profiling execution without halting. You can capture complete execution history leading up to a crash, crucial for rare faults after many hours in the field. This is the visibility a professional needs to guarantee product stability. A typical Arduino prototype starts small. It might have one sensor, one actuator, and a simple user interface. In this environment, the code is straightforward, and the interactions between components are easy to manage. The Arduino framework and its libraries work beautifully at this scale. However, a real product is often far more complex. It may need to manage multiple communication interfaces like Wi-Fi, Bluetooth, CAN bus. It may also need to read from a dozen different sensors, control several motors, provide a responsive graphical user interface, all at the same time. As complexity grows, the limitations of the simple Arduino sketch structure become a significant problem. Without a clear software architecture, the code can quickly become a tangled mess of interacting parts, often called spaghetti code, The hidden actions of different libraries begin to cause conflicts. One library might overwrite the timer configuration of another. A blocking driver for one sensor might prevent the system from servicing a critical communication link in a timely manner. These integration issues often do not appear in simple tests, but emerge when all subsystems are running concurrently. To manage this complexity, professionals use a layered approach. A hardware abstraction layer, drivers above it, and an application isolated from low-level details. For highly complex systems, Many engineers use an RTOS for tasks, scheduling, and safe intertask communication via queues and mutexes. This structured approach is essential for building scalable and robust embedded systems. When professionals move beyond the prototype phase, what do they use instead of the Arduino ecosystem? The process starts with selecting the right microcontroller for the job. Instead of being limited to the ATmega 328P or SAM-D21 on a typical Arduino board, they have a vast market of options. STM32 family from ST Microelectronics, Raspberry Pi RP2040, NRF series from Nordic Semiconductor, wireless, MCUs from NXP, MCUs from Microchip, MCUs from Texas Instruments. These MCUs offer a wider range of peripherals, more advanced power-saving modes, and better documentation. Professionals work directly with the manufacturer's tools and documentation. They do not rely on simplified Arduino libraries. They read the MCU's datasheet and reference manual, often hundreds or thousands of pages, to configure clocks, timers, and peripherals. They use vendor IDEs like STM32Cube IDE, NXP's MCU Expresso, or third-party toolchains from IAR or Kiel, plus code configuration utilities. They choose a software architecture appropriate for complexity. For simpler applications, bare metal code offers maximum control and minimal overhead. For multitasking systems, they integrate an RTOS like FreeRTOS, Zephyr, or ThreadX for scheduling and resource management, improving reliability and development time. Finally, the hardware is designed from scratch. A custom PCB is created using professional EDA tools like Altium Designer, KiCad, or Eagle to optimize size, shape, and cost. Components are placed to minimize noise and improve thermals. Features like ESD protection, proper filtering, and test points for manufacturing are included. This comprehensive approach, specific MCU, professional tools, robust software architecture, and custom hardware defines professional embedded development. Moving from an Arduino prototype to a professional product does not mean throwing everything away. The prototype has immense value. It proved that the core idea is feasible. The transition is a process of systematic refinement and hardening. Many successful products began as a tangle of wires on an Arduino breadboard. The key is a clear plan to meet production requirements. This involves a deliberate rework of the hardware and a deliberate rework of the firmware. Keep successful prototype concepts while building a more robust foundation. The first practical step is to rewrite critical sections. Identify code that uses delay or other blocking functions and replace them with state machine-based, non-blocking logic or timer-driven events. Dive into the microcontroller's datasheet and learn to configure hardware timers and DMA channels directly. This will give you the deterministic timing needed for a reliable product. Start by replacing one library at a time with your own driver code. Incremental changes are more manageable than a full rewrite. Next, focus on hardware. Create a schematic for a custom board, even if you use a dev kit next. This forces you to think about every component. Choose a suitable voltage regulator based on your power budget. Add dedicated SWD and JTAG connectors for proper debugging. Include decoupling capacitors near every IC. Consider basic circuit protection and add test points. Let this initial custom design serve as the blueprint. Build a test plan from the beginning. Write unit tests for drivers and run integration tests early. Test your comms while a motor runs and a sensor is read. Use a logic analyzer and oscilloscope to verify timing and signal integrity. Continuous testing finds problems early and cheaply. The Arduino platform is an unparalleled educational tool and a brilliant environment for rapid prototyping. Its ability to get ideas working quickly is a superpower. It has democratized electronics, empowering a generation of creators. There is no shame in starting a project with an Arduino. In fact, it is often the smartest way to begin. It allows you to validate core concepts and demonstrate functionality without low-level overhead. It serves as an electronic sandbox perfectly. However, To ship a robust, reliable, and cost-effective product, you must eventually graduate from that sandbox. The very abstractions that make Arduino easy become liabilities in production. Commercial products demand control, predictability, optimization. Engineers must take direct ownership of hardware and software. This means managing design intent, guaranteeing deterministic timing, engineering for low power, using professional debugging tools. The journey from an Arduino prototype to a production-ready system is a critical step. It involves replacing the convenience of libraries with the power of datasheet-driven design, moving from a pre-made development board to a custom PCB, shifting from simple print statements to hardware debuggers. This transition is not a rejection of Arduino, but an acknowledgement of its purpose. Ultimately, the trade-offs favor simplicity and accessibility at the start and deeper control for products. Which problem do you meet first? Timing, power, or debugging?